They just replaced Igor Danielkin and Cesar Fernandez. Cesar started a faculty job in Mexico, so hopefully we'll get also Mexicans on board. And we have also people from postdocs at Indiana, Vincent, who of course you know, and Ina is working with Emily Passemark, who is a new faculty member at IU that we were able to hire because of this initiative. Here you see a group of happy campers at one of our weekly meetings. On Tuesday we start at 1 and we end up when we basically all completely exhausted. We have people joining by Blue Gene, for example, Misha Mikashenko, who is a Compass collaborator, experimentalist, is working with us on a essentially daily basis. In particular, he's working with Andrew Jakura, also a PhD student at IU, on analyzing free Pi production. Oh, so this is sort of in NSF's nomenclature. These are our products from the last 3 years, brief summary. So we essentially have of the order of 40 papers published, over 100 talks given by JPAC members on JPAC-related physics or activities. We are producing these web pages, which Vincent, I believe, is going to show how they work. This is one way of how we envision the interfacing between theory and experiment. Publication is, we also have about 10 ongoing analyses where theorists from JPAC are really participating with experimentalists on helping with analyzing data and interpreting the result, and that includes several class analysis and also Compass analysis, but also LHCb and BESS. So this is just a snapshot of a website. Again, Vincent is going to talk more about it, but again, essentially once a paper is written about a physics and associated amplitudes are constructed, then we go one step forward, put all the information into these website templates, including possibility of running the codes, downloading the codes. The codes are written, well, we try to write this in many languages as possible, even this is not necessary because we know that AMP tools can read Fortran, AMP tools can read C and C++. But there are typically 2 versions of the code. Again, all the detailed explanations of how to run the code, how to change parameters if you want to fit, how to simulate data with it, it's all included there. As I said, Vincent will show you more about this. So this is just an example. Again, as I had on the previous slide, we have something like 30 or 40 papers on specific processes. So I'm not going to go in much detail before I run out of time. This is just one example. We've done very sophisticated, one of the most sophisticated analysis, I would say, up to date on things like vector meson omega of phi decay into 3 pi's, in which include things which, in standard nomenclature would say go beyond the Eisenhower model, where, for example, a rho meson here in the intermediate state that decays into 3 pions, and these 3 pions can rescatter and so on and so forth. So this is these type of amplitudes are written, constructed based on principles of the S-matrix theory, including unitarity, analyticity, and so on and so forth. And we are, as I said, for example, working with Volker here and Carlos on implementing these analyses in class, these amplitudes in class analysis. One of the results of this analysis, for example, is this type of analysis directly related to transition form factors, for example, between a phi and a pi 0, radiative transitions, basically the same type of physics that goes into the free pi physics goes into this transition form factor. So we made a prediction, well, this is Igor Danielkin's work, made a prediction for what this transition form factor should look like, and there's this is consistent with the Chloe data, as you can see, and it's somewhat different from vector meson dominance. It's clearer, closer to the data. So these effects that really take into account the scattering in pions.
So the gray is the vector meson dominance. And
this is vector meson dominance, and the solid line is the prediction.
And the dashed?
And the dashed, I don't remember. Okay, so now to the main topic of resonances. So here, of course, you recognize the delta plus plus. So let me make some general comments or statements about what resonances are. So in non-relativistic dynamics, resonances are sort of external. I mean, what really, are the product of the dynamics that you put in. And you put in the dynamics for potentials. Okay, so the fundamental thing would say is a potential, and then you get the resonances out. Now, in relativistic dynamics, of course, the notion of potential doesn't exist. Because resonances, the resonances, all the particles are sort of created equal. So you could think of a potential, and that's sort of what we learn in first courses of how strong interactions work, how nuclear physics work, is that you get potentials by exchanging particles. You can exchange, for example, you have an attraction by exchanging sigma mesons or exchanging pions. But again, the same things that you exchange can be produced, and then you sort of lose the distinction between a resonance, or something essentially a bound state or a particle, versus a potential that can produce that particle. But again, fundamentally, there is no way of introducing the concept of a potential into relativistic theory, so there has to be some other tools to attack the problem. Now, unfortunately, as I'm sure you're all aware, we don't have such tools. There's no first principle mathematical analytical tool that basically solves the field theory. Now, of course, there are ways of simulating the field theory. This is what we heard from Joe. But this is, again, not really solving the theory. It's not getting all the properties of matter out. So the way to essentially get a content of what the underlying physics predicts, basically by sort of trial and error. Put resonance in and see if the data requires that. And that's also what essentially happens when you analyze lattice simulations now. When you're on the lattice, you're simulating a scattering experiment. You extract the physical information out of that lattice data by assuming some theoretical description of the amplitudes and see if it fits the data, or whether the data can discriminate in various hypotheses on what the amplitude contact might be. Again, so the two different philosophies, the quantum field theory versus S matrix. So, when everybody takes course these days in relativistic dynamics, relativistic field theory, and of course the idea is that you start from something fundamental, from bare particles, then you dress them up, and hopefully you work out and solve everything that find out everything that these bare particles can produce. Now, this of course doesn't work. It works only at perturbation theory, but that's pretty much it. All the really interesting phenomena, I would say, come outside of perturbation theory. And I would say it's a pity that the typical quantum field theory classes essentially are 100% dedicated to perturbation theory, and not all the really interesting physics that is there in field theory. But of course, this is because, as I said, we don't have the tools, so it's difficult to teach something if you don't have the tools. And that's essentially the only one tool that we do have. So the S-matrix philosophy is that basically you start on physical observables, and you explore the properties, the general properties of the amplitudes first. And those general properties of the amplitudes are in principle very simple, but they have dramatic consequences. Now, they don't give you the whole story, as I will illustrate in a moment, but they are sort of the foundation for how to look for the dynamics that you cannot really calculate based on first principles. And those fundamental constraints, or those fundamental properties, are analyticity, which essentially says that functions are scattering amplitudes are smooth functions of Mandelstam variables. So here again, I want to point to one thing, that the Mandelstam variable, so the amplitude is a function of Mandelstam variables, is the more fundamental quantity compared to partial waves. We typically tend to forget about this, because of course when we think about resonances, it's the partial waves that we're interested in. We tend to think, oh, let's build partial waves. But really most of the constraints start from here, imposing the constraints on the full amplitudes. In fact, partial waves are much more complicated, of course. The constraints from the S matrix on partial waves are much more complex than they are when it comes to full amplitudes. And, well, what does it mean? Well, if everything was completely smooth, was analytical, then there would be nothing left. So there has to be some singularities of the amplitude, and the singularities are also in principle very simple. They are always related to a physical process, and the only physical process that you have are basically particles. So you're producing particles, and production of particles is manifested as singularities in the amplitudes. Bottom line is all the students really have to go back and take complex analysis class.
So is the amplitude just the sum of all these partial waves?
Yes. One way to, of course, a relation between these two is a series. But again, the series converges only in a certain domain. And it's when and singularities are manifestation of when the series does not converge anymore. And again, it is the singularities that one's primarily interested in when it comes to analyzing amplitudes. Okay, so here is a quick illustration. Okay, so again, we talk about bumps and peaks on the real axis. How is that tied to complex analysis? Well, if I see a bump here, that means that if I could add an extra dimension, then bump is just a projection of maybe a higher bump in the extra dimension. Eventually, if you go into the extra dimension, the bump becomes a singularity. And the extra dimension is basically the complex direction. So everything that you see, bumps and wiggles and cusps, etc., they're always manifestation of singularities. And it is those singularities that we are after. Those singularities live on something which is called an unphysical sheet. In what sense it is unphysical? It is unphysical in the following sense. I hope this is not too complicated. I've tried to take as simplest function as possible, which actually is related to very much to what we're talking about here, is a square root. Square root is the thing that drives particle production, is the threshold. So a square root function has such properties that, for example, if I take specific value 25 plus a little bit I epsilon, then the value is minus 5I. But if I take minus I epsilon, the value is plus 5I. So I change the imaginary part by a bit, and the function changes dramatically by a factor of 25I. Now, experiment is done here. Okay, so experiment is done on what's called the upper lip, if you wish, of the unitary cut. So this is a real value of energy plus a little bit. And for example, if I was to continuously change energy, I would go, for example, from 25 to maybe 10, all around here, and come down. I'm not very far in terms of the real value. It's still the same. The imaginary part is infinitesimally different, but the value jumps by a lot.
Can you orient me on what's the vertical axis here?
Vertical axis is the imaginary part of energy. This is the real part of energy. Okay?
And where's zero?
Zero is here.
The pointer's moving around. Zero's where the zero
Well,
is, or zero's where?
It's artificial here. Imagine the threshold was a zero. Imagine you were producing two massless particles.
Okay.
And this would be the threshold for production of two massless particles.
And those two lines, what are they?
I'll count the two lines.
Okay.
So the two lines right now, what they are supposed to show you is that if I approach the real axis, that's where the physical energy is. From slightly above, I'm approaching something like minus 5 times I for the value of the amplitude. But if I was to approach the real axis slightly from below, my value would be plus 5I. Which one is right? Okay? There's only one which corresponds to the physical value of the amplitude. The one which is the physical value of the amplitude is here. Okay? But the amplitude has this weird property that it has a very different value if the imaginary part of energy changes slightly. What that is referring to as there being a cut. That the complex S-plane is cut, and this is sort of this shape here represents a cut, a hole, if you wish, in the plane. I've exaggerated it because the hole is infinitesimally small, but it simply tells me that the value of the amplitude, I cannot, going all around here, the amplitude changes smoothly. If I walk around here, the amplitude changes smoothly, but if I want to cross the cut, the amplitude will jump. That's called the first sheet. Now, in complex analysis, if you are in the plane of the argument, in this case energy, over which the amplitude changes smoothly, so I can walk around all the way here, the amplitude changes smoothly from one point to the next, I can use Cauchy's theorem. Okay? I can use Cauchy's relation to establish connection between amplitudes at one point and the next. But it all happens on what's called a physical sheet. Okay? That's where the amplitude changes smoothly. And I cannot include anything here because that's where the amplitude jumps. So I could write Cauchy relations that are everywhere here, but have to avoid this cut. It so happens that nothing really happens here on the first plane. You don't see any resonances, you don't see any singularities, because as I said, the only singularities of the amplitude are these type of branch poles, which are related to particle production. So there is nothing else happening here. Whereas the interesting physics is when you now ask the following question: can I do the following trick? Can I suppose I have the amplitude evaluated here on the upper side. Is there a way of somehow changing the function continuously so that I am allowed now go under the cut somewhere else in some other plane, which is called the second sheet, so that the amplitude changes continuously as opposed to jumping? So here I'm writing, for example, if the function is this, then I change a sign here, and this function, when now when s is giving a little bit of I minus I epsilon, then suddenly the value is not plus I epsilon, it's minus 5 I epsilon. So the value of, so I can match this to that, and these two functions will now change continuously as I move from up to down. Okay? But it's not the same function anymore. Okay? The function that I started with is the red one. Now I sort of glued in the blue one. And the blue one with the red one now change continuously as I move across the real axis. Is it unique? Is there only one function that has this property? The answer is yes. So in principle, if I know the function here, I know how to find out this other function that I glue in continuously, which really tells me how the function changes all over the place. Okay? And it is that second function that if you were to continue down, you will find a singularity. Okay, so that's the type of singularity. That's the mathematics we look for. Okay, so here's an example. A deuteron. Okay? So what is a deuteron? So we're going back to potential physics as an illustration, but the same properties of the amplitudes translate in relativistic physics. Except that we cannot associate it with specific potentials, but the singularity structure is almost identical. So here is S is essentially the invariant mass of proton and neutron. This is the 4-nucleon mass square. Suppose I cannot make a measurement in which the invariant mass of the energy is less than 2 masses of the nucleon, so I could make an scattering experiment and measure the amplitude somewhere here. But you see, well, this is a function that likes to do something. If I could continue this function where I cannot measure it, this function wants to grow. And it is the manifestation of the fact that indeed, if this function is an element of a complex analytical function, then this complex analytical function outside the physical domain, which is here above threshold, has a singularity. And that's the deuteron pole. So the deuteron pole is on the real. I told you there's nothing on the real axis. I misspoke, except bound states. Okay. So deuteron is a bound state of proton and neutron and appears as a pole on the real axis. Now, if I make a model in which this deuteron is essentially coming out as a solution of a Schrodinger equation with some simple square root potential, then this is a potential that binds my proton and neutron and produces the deuteron bound state. Suppose I decrease the potential a little bit. Well, the binding is not enough, and at some point the deuteron is not formed. What happens to this pole? The pole, as this thing decreases, well, what will happen? This pole is going to move to the threshold and then dive in onto the second sheet. It will disappear. So you will not see that on the real axis. You will see it as a pole on the second sheet. So it is, you can think it's the same pole, it just continuously moves around the complex plane as you change the physics, as you change the mechanism for what generates that singularity. Now, how is it seen on the data, if you wish? So we measured this part, but this part is a manifestation of a singularity here. As the strength of the potential is decreasing, this singularity comes in closer, this big peak comes in closer over here, and then it disappears. It dives into the second sheet, and then that's why we see a cusp. You no longer see a singularity because it went away. Okay, so that's the cusps that, for example, you heard about from Joe's talk yesterday. They're typically manifestation of such an effect. That an interaction is almost strong enough to produce a bound state, but not quite. Okay. I know how much time I have. probably nothing, and I only got started.
You can take
10 more minutes.
10 more minutes. Okay, so in the old days, people thought that basically just looking at the amplitudes, imposing the S-matrix relations and Cauchy relations would in principle tell us about these singularities. Because I said if there is a unique continuation of the function, then you could imagine that knowing the amplitude everywhere here will determine what happens down there where the interesting things are, like the resonances. Okay? So that was the idea. Try to impose as much as you know on the first sheet where, for example, measurement takes place. So the value of the amplitude here is determined by phase shift, by experiment. Then use Cauchy principle to evaluate the amplitude everywhere, and then continue down, and hopefully this will tell us everything about the singularities. And this was, I'm not going into details, but one of the constraints, for example, is the unitarity, as I'm sure you're aware of. Unitarity is telling us about the jumps across those cuts. Once you know that, then there are more cuts. Now we're talking about partial waves, so there are cuts on this side. This is a cut of the full of the amplitude. But as I told you, partial wave amplitudes are much more complicated. They have more cuts. So partial wave amplitudes, for example, also have cuts on the left-hand side. And the physics origin of these cuts are exchanges, are potentials. So everything that happens everything that is exchanged in the T-channel in the partial wave produces a cut on the left-hand side. All that has to be put in when you build a dispersion relation. Basically, you're reconstructing the amplitude via Cauchy theorem, and that's what you end up with. You end up with typically with a relationship like this, which basically tells you amplitude anywhere on this first sheet is determined by its discontinuity, which is related to the amplitude via unitarity, plus anything on the left-hand side, which is basically the potential. So effect of sort of like a potential theory. Here it is. In principle, we say, okay, I know this relation. It looks sort of like a Schrodinger equation in some sense. If I input this, if I give you some function over here, that looks like an integral equation for A that I could solve analytically or numerically maybe, and then continue down this cut to the second sheet and see if I find resonances. Typically what happens is that you don't find that. That this thing is, if you think of that as a potential, the potential is too weak to bind. Okay? So it's like, this virtual state, in the case of the deuteron, the potential is not strong enough to bind your two pions to produce a rho meson. In other words, I could think that I could exchange a rho meson, that's like a Yukawa potential for two pions, and that is enough to bind my two pions and produce a rho meson again, just like the deuteron. It typically doesn't happen. Okay? So where do the resonances come from? Well, they come from physics that you have to put in by hand. Okay? So it's not sufficient to just know the meson-meson interactions or the meson-baryon interactions, typically, to reproduce the QCD spectrum. Okay? So something is missing. Now, how can that be missing? Because I could say, well, if I know all the interactions, I know entirely everything that goes into this equation, that's an equation. I have a solution. I know how to analytically continue. I should be done. The point is that this equation does not have a unique solution, for example. And the ambiguity in that in this equation is a manifestation of the physics that is missing when you think of rho mesons, for example, being generated just by interaction between two pions. In practice, that's equivalent to things, for example, like K-matrix poles. Okay, then in the K-matrix, we're not talking about features of the K-matrix that have to do with pion-pion interaction, for example, pi-eta interactions, but we put some parameters in the K-matrix, and those parameters are essentially manifestation of this non-uniqueness here. In other words, something been missing. There's fundamental theory out there that is not constraining the first sheet, what happens on the first sheet in such a way that you know exactly what happens on the second and third and so on. So this should not be considered as an equation for looking for bound states or resonances. It should be considered as a constraint on testing. I need a resonance. So I create an amplitude with the right number of K-matrix poles, for example. I better do it in such a way that this thing is satisfied, and then test my hypothesis about how many poles I put in my K-matrix against the data, whether that can discriminate whether I need one pole, two poles, or what else. Okay, so this is how people thought it's going to work, but it didn't work. So in '62, they thought that they will solve QCD by doing this bootstrap type calculations, but it was realized that they don't have unique solution, and the things that we were finding out are not really representing the spectrum. Okay, so what's the strategy? Again, so we need to put resonances by hand. So we need some prior knowledge about where they come from. Quark model lattice, for example, the lattice spectrum that Joe was showing in one of the first slides that everybody showed. He was very carefully saying these are not the states that you see are not exactly the states that QCD has, but they very likely may be an indication of there being a state. So this is the type of information that will go into building parameterization of amplitudes and then fitting the data. There is another thing another of these constraints that is often overlooked. The constraint is the duality between resonances and regions. I'm not going to go into much of the detail, but just to make you aware that this constraint is going to play an important role in what we're doing. Not to just think of resonances as individual objects, but resonances as members of a much wider class of things which are called regions. And regions are basically collections of resonances. And typically what you see is something which is called the Fauci plot, which is just one aspect of what region physics is about, which to some extent is essentially a plot of a spin of a resonances versus its mass. But again, it's only within some approximation of what it is. But even in that plot, you can already discriminate various physical phenomena that are happening. Imagine that QCD was 100% confining. There means no decay. So if everything is confined, they cannot decay. So everything is a bound state. You could create as many bound states as you wish, and this plot will essentially continue going on forever. If QCD, at some point, resonances can fall apart, because strictly speaking, QCD is not confining, because indeed, things can fall apart, then at some point, you cannot create bound states with too much angular momentum, because angular momentum barrier essentially repels things, it works against binding, and therefore the register trajectories are going to curve. So they're not going to keep on rising forever, they have to curve, and there's going to be some saturation as to how many J's can exist on the trajectory. Okay, so again, this is just one element, one aspect of the physics that you can learn from this duality. I'm not skip this. Okay, so now what's the sort of plan of attack? So the first thing that we need to do for an experiment like GlueX is to establish that we can separate the physics that we're interested in from the backgrounds. Now, somebody's physics may be somebody else's background and vice versa. So if we are interested in mesons, for example, we want to be able to isolate the forward-moving system from the recall. So the first thing that we need to establish is that the full amplitude, which in principle has two particles coming in, photon and the target, and say 4 particles being produced, really can be separated into these two sort of phenomena. That you have a scattering of a beam on something else producing, say, 2 particles. That something else is a region, of course, as you know. And at the end of the day, we need to establish that this phenomena happens. So that's one aspect, part of the story. Once this thing is established and this process is isolated, then it so happens that the scattering of a particle in the region, which, as I said, is collection of resonances, it really has properties that are very similar to scattering of a particle in a particle. So we know how to handle this object, even though this is not a physical particle, even it's a collection of particles. Then, of course, we are interested in looking inside of that. And again, various processes can happen. We can have resonances being directly produced, or you can have this exchange effects. And again, how do we disentangle one from another? So again, I hope Vincent will have time to talk about how to disentangle regions. So maybe I'll just talk 2 words about the upper block. Once we've established that there is a region exchange, how do we isolate an exotic? So here is a compass data. So this is a work in progress. This is what Vlad Pauk is essentially focusing 100% on, is to be able to essentially to understand this type of process. I'm using here Pomeroy because he specifically started working with compass data. Because there is already compass data. There's lots of compass data. So all these techniques you can test on compass. Then the idea will be to exchange pion beam with a photon beam, and then of course we have more than just a Pomeroy exchange. So first we want to establish that this thing happens so that we really have a pion-Pomeroy scattering. I'm sure you've all seen this plot. So this is a plot of invariant mass of the eta pi system versus the scattering angle between the pion and the Godfrey-Jackson frame. So this thing here corresponds to forward moving pi. So again, we can think about this. So this is two variables. And if we really manage to isolate pi and Pomeroy scattering, it is a function of two variables. We really talk about function of two variables, pi and Pomeroy scattering going to pi and eta. The two variables being, for example, t and invariant mass, or mass and cosine Gottfried-Jackson. You see here, you see two features, well, several features. As you go up higher in mass, you see this peaking. You see events here and you see events there in forward and backward direction. That corresponds to these type of exchanges, T-channel exchanges. So you in the forward direction, you either have, for example, Pomeroy on the F2 being exchanged, in the backward direction you have the A2 exchange. This is regiophysics operating here. In this mass region, of course, we have the resonances. You see primarily the A2 band here, more or less symmetric. But of course, there is some asymmetry, and the asymmetry is the P wave. That will be the exotic wave. Now, how do we approach this? Well, as I told you, amplitude is a continuous function. So whatever happens here must know about what happens here, and vice versa. So the best strategy is not to basically close your eyes and just look at partial waves in low invariant mass and forget about what happens in higher mass, but really take the whole thing into account and be able to continuously match whatever you think the resonance content is at low mass with what you know about production at high invariant mass, which is related to these exchanges. For example, one thing that you'll immediately learn from these processes is the following. These are the dominant exchanges. These are the things that I expected to produce these bands here. Now, most of that is symmetric. So if I look at the symmetric combination of the amplitude, is sum of all these exchanges, so it's Pomeroy, F2, and A2. If I look at the difference, then Pomeroy and F2 do not change sign. The A2 changes sign. Now, the properties of the F2, A2 and F2 are very similar as mesons and also as exchange object. So basically in the difference, they largely cancel. So the contribution of F and A2 largely cancels in the difference. So if there was no Pomeroy and they were indeed identical, this plot should be exactly symmetric. There should be no exotic. So you may think that maybe exotic somehow, the asymmetry, which at lower masses is traced to, for example, the P wave, the exotic wave, is somehow related to the presence of this extra bit, which is the Pomeroy, which sort of makes sense because we expect exotics to have gluons, Pomeroys have gluons, so there may be some underlying dynamic correlation between the two. So the rest is sort of mathematics, and I'm not going to go into details, but again, you like the variables, as you know, this is a function of 5 variables. We want to reduce it to a function of 2 variables. So here is the regio part, which again, we need to prove that this reduction happens. The dependence on 5 variables that you measure exactly in the experiment can be parameterized as essentially products of objects that depend specifically on selected parts of those 5 variables. That's what we want. That's what we need to test. And then we need to implement this complementarity between the low mass region and the high mass region, which again involves matching various variables. And this is highly non-trivial, believe it or not. It's actually going to be the first time that this type of process, that this type of approach is going to be applied in analysis of these 2 to 3 reactions. Not only on, theoretically done, but also experimental. It hasn't been even done theoretically, basically. So there were some papers in the 70s where people started to think about how to do this. It's being done in things like 2 to 2 processes, like pi nucleon scattering. For example, when you relate pi n resonances to regions in the pi n system at high energies, but it's never really been done in 2 to 3. And we have cracked that recently, how to do that, basically.
Is that 2 to 2, or where is the 2 to 3?
This is 2 to 3 because the underlying process is 2 to 3.
Oh, 2 to 3.
It's 2 to 3. And this matching, at the end of the day, does need to know something about these other variables which are present in the full process, but not part of that. Okay? So it's sort of, you could think of that it's sort of done, it's not quite correct, but you could think it's sort of done in bins of one of these variables. It's not exactly in bins, but it knows about this thing originated from 2 to 3. Okay, so I'll summarize, as I said already, we're doing this we're cracking this with an eye on analyzing compounds, but once we've cracked that, then it should be much more difficult to write the amplitudes and do it for GlueX. The idea would be eventually is to be able to implement this type of constraints which relate to whichever way you parameterize the amplitude in the resonance region and how you parameterize the amplitude in the high mass region in things like amp tools during the fitting process, so that when Minuit fits and changes parameters, this constraint is implemented as some sort of a penalty function, for example, that you don't arbitrarily change parameters, but you do it in a way which consistently satisfies these things which are called finite ensembles. All right, I'll stop here, so that this still has some time.
All right, thanks, Anne. Anybody have any questions?
Can you go back to your slide with the 8up?
Which one?
The
Previous
compass
one?
data with the 8up. Yeah, there you go. Great. So I'm thinking about GlueX and what the invariant mass reach is in GlueX, which is probably like up to 2.5 to 3 GeV. How critical? Well, I guess we don't know until you do the experiment. But I mean, here obviously a huge advantage is to be able to look
Because you have
at
the
between
right,
3 to
right.
5. And try
Now,
to extract
even if you
that.
don't know that, if we don't have the data, we have the theory, if you wish. We know what should be happening here in the high mass region. I mean, because for that we have essentially the regiophysics is telling us what the amplitude should look like here. So we would use that still as a constraint, even without the data.
Yeah, but presumably you'd like to have the data that really helps.
Ideally, you like the data, absolutely.
Great.
So let's say, so you were saying you can't completely solve the system of equations for the amplitudes because there's still
There are basically two things. Okay, sorry, I interrupted you.
well there's still a lot of solutions. The solution's not unique. So if you had information about things like, the row resonance pole, etc., how much does that help narrow things down a bit?
Right. Several things. The equation that I wrote is the most simplest one you could think of in the most simplest physical scenario, which is, a drop in the bucket of the type of processor we were looking at. So we don't even have an equation. I mean, when we look for things like writing something like this for 3 pi or 4 particles, a process involving 4 particles, it's not even going to be practical. Now, as I said, people in the 60s that were exploring this, and they were indeed going beyond the simple equation like that and making it much more complicated, they figure out that basically, it's a hopeless problem. It's unconstrained. You cannot think of that as a mathematical equation with a unique solution because there are so many ambiguities. Forget about it. Now, the benefit that we have is that we know there is QCD, and what we have learned indeed is that the effects of hadron-hadron interactions, except for a few remarkable cases, are not the ones which are responsible for existence of resonances, at least most likely not the ones that we think are there based on the quark model. So we shouldn't really be focused on the negative here with there not being a first principle equation. We have other information that is probably much more valuable for what we are aiming, and the bits and pieces of this equation, which essentially go into all the constraints of the S matrix, we can still use, and we will use.
Any further questions for Adam?
And maybe just to make sure I understand, maybe you mentioned for GlueX it will be more complicated, but it's just due to the fact that you have more regions contributing.
That's right, and you also have polarization of the photon. So kinematics is...
But this should help also.
Sure, it's more complicated from the point of view of the structure of the formulas of the amplitudes that you have to write down.
Everything goes
up. Everything gets bigger, if you wish. And and ideally you need more than one postdoc to work on it so that somebody can check. Because the devil is in the details, and it's not as fundamental.
Can you, in the last, your last slide, you show for GlueX, so this deck kind of diagram,
Yeah,
right?
this is what's called double wedge, but you call it.
Right, yeah. How would be incorporated?
Well, that's exactly what I was referring to here. The way it will be incorporated is via these constraints. So, again, strictly speaking, representing whatever complicated physics happens when you have photon-proton going to, say, free particles, by these simple diagrams, it's only true in certain kinematical domain. Okay? So, and the certain kinematical domain is, for example, when this invariant mass is large and this invariant mass is large, this momentum transfer is small, this momentum transfer is small. Now, that's not the region that we are interested, that has simultaneously resonances in. The region that has resonances in is where, for example, pi eta invariant mass is small. So that region, basically, you could say to 0 4 that doesn't overlap with that region. But nevertheless, the amplitude has to change smoothly from one region to another. And that's what you want to use. So even though you are measuring the amplitude in the low eta pi invariant mass, you want to use the smooth continuation to the high mass region to constrain how the amplitude looks like in the low region invariant mass. You implement this via these mathematical relationships. So for example, on the left-hand side here, there's going to be, this is just a schematic representation. Here it is. So on the left-hand side, there will be an amplitude which contains information about resonances. On the right-hand side, there's information of the amplitude that is the deck. And you see they are evaluated schematically in different regions. One is sort of integrated up to a certain value, the other is integrated above that certain value. So they are in the not overlapping kinematical domain, but existence of such relation is because it's one function. Okay? So for example, we make a model for this, like model of a deck. We make a model of this, which includes parameters of an exotic, which we don't know what they are. Those are the parameters that will be fitted. We fit this amplitude to the data, but every time we change the parameters of the exotic, we make sure that left equals to right.
How important for GlueX is double region exchange?
How important? Well,
I mean, because it's lower energy as compared to compass. For
well,
example,
you see it here. This is you see clearly a different physics here versus here. This is the physics of the direct resonance production. This is the physics of the deck, if you wish, a double region.
Coming back to the comment you had before,
That's right.
Answering to Mezzo.
So it's the energy range. It's how much you can open up the eta pi invariant mass.
But you said it's still important, or at least you should put it in because it gives constraints, even though the high and very mass
It is.
range is
What I'm saying is that this distribution here plays a role of what happens here. Even though it's outside, it's in the different kinematics. Because the smooth function, you cannot happen that something over here does not know what happens there and vice versa. So you cannot simply say, okay, because that I'm going to describe this by this. Well, it doesn't work. It's a completely different distribution. But because of the connection, if you know this, then you can constrain what happens there. If you have the data, better. If you don't have the data, you have to use theory to tell you about this distribution, the high mass range.
Okay, so we should probably move on to business talk.
Thanks, Adam.